Good morning, everyone. Can you please confirm if you can hear me? Let me ask a question as well. Can you confirm if you can hear me? All right, please answer the poll. Awesome. Bunny would join us shortly. Perfect. Everyone can hear me. And how is it going with you guys? Are you enjoying the sessions? All right. I guess all of you are enjoying the sessions. So let me do one thing. Yesterday we had a quiz and many of you participated in the quiz. So what I'm going to do is I am going to quickly pick a random winner, and the winner would be picked completely in random. So we are going to use Google's random number generator to do that. So what we had done is we have basically compiled a list of all the people who have participated in our quiz. And yesterday, about 196 people participated. So, what we are going to do is, out of the 196 people, we are randomly going to pick one person and then we are going to give them a surprise gift. So, for this, I am going to use something called as random number generator. So just to show you guys whether it's working or not, I have put a minimum of 1, maximum of 1000, and I'm clicking generate. You could see that it's generated a random number. How? So the moment I click the button generate, a random number is generated. So now we have 196 people participated. So that would be minimum of 1 and the maximum of 196. Just to make sure, yes. And now let's do this. 3, 2, 1, and go. So number 145 is the winner. Let's see who that person is. Supriya Shivapuja. Congratulations, Supriya Shivapuja. You are a winner for today. And our team will get in touch with you and we will tell you how you can get your free gift card. And congratulations, Supriya. And even today, we are going to have we are going to post questions after the session onto the WhatsApp groups. So please participate, and we will do the quiz competition. We will pick the winners on Monday. And
Yep.
over to
Thank
you.
you. Thank you so much, Enoch. Enoch, one more thing that you might want to do. First of all, congratulations, Supriya, on winning this. We truly appreciate your participation in the quiz. And this is one way to ensure that we all bring you onto the digital platform because we are in the emerging technologies. Right? And recorded videos, we have placed the YouTube link on the sticky note. You just need to click on that and you'll get access. We are creating the thumbnails to each and every video so that you understand on what concepts are covered in each of these. So yeah, I think Enoch is working along with Shubha to get the thumbnails ready, and thumbnails would be available so that, I mean, a few of you all were giving this suggestion, so we will certainly take it, and that's their on cards. We already are aware of that. We will do the, we'll add relevant keywords to the videos so that when generally when you search, you get that in the result. Okay, so once again, if a few of y'all are saying that, you know what, chat window is filling up and we are unable to see the, YouTube link, we are posting it here once again for y'all. If you still are not able to see, because a few of y'all would be joining in a little late, so after the break, once again, I'm going to post it. Okay, so let me share the screen and welcome to the faculty development program on AI and deep learning, which is launched in collaboration with AP State Skill Development Corporation. AP State Skill Development Corporation and 360 Digit MG is bringing you this AI and deep learning training, which is for 60 hours. And yep, so let us get started. As usual, we will go to our mind map and we shall quickly do a recap so that you all understand on what we have done, what we are going to do, right? And here we have supervised learning, predictive modeling, neural network, convolution neural network, and you have CNN here. Okay, and this I believe is will be updated today. Yeah. Okay. So just give me quick minute. Sorry, just quick minute. Okay, let us proceed further. Positional argument follows some error, right? Sure, we will look into that, Anil. Yeah. You can post this error. There are multiple ways to reach out to us. Just go to our LinkedIn or Facebook, post it there in the group, not on the page, in the group. And then we will respond to that. Yeah, that's one way to ensure that constantly we have the engagement on. But let us do a quick recap and then we'll proceed further. So we started off by discussing about project management methodology, CRISP TM, understanding the business problem, recording the objectives and constraints, collecting the data based on various data types, then data cleansing or preparation, exploratory data analysis, feature engineering. Once you are done with this, you proceed further with data mining or machine learning. But even before we got into this, we discussed about deep learning primer. We discussed about mathematical foundations. What are the practical issues that we face? How do we counter that? And then we have done a thorough deep dive into perceptron algorithm and multi-layered perceptron. Perceptron and multi-layered perceptron. And then we switched our gaze. In this, we have solved a use case wherein we wanted to measure or we wanted to predict the loan defaulters. If you remember the use case, how do you predict on whether someone is going to default on the loan or not? Okay, in this MLP. Loan defaulter prediction model. This was on structured data, wherein we had data in neat rows and tables, and we could solve this. Once we solve that, we understand how to deal with the regular data or the structured data. So henceforth, if you have data coming in from our DBMS, you know on how to handle that. Okay, it's not about how many you do, how well you do. That is important. Even when it comes to entrance exams, be it IIT JEE or be it GMAT or GRE or GATE or any entrance exam, you don't do the same thing again and again. We learn different types of questions in the same type. Even if you solve 1,000, how will it help? It will not help, right? So we have done this. So we understand structured and RDBMS. Now we need to switch gears. We cannot still hang on to the same structured data because 80% of the data that we have on the planet is an unstructured format. For this unstructured data, we first have looked into images and videos. Okay, and this was the traditional way of dealing with your images, like your Adobe Photoshop or Microsoft Paint. All these use these kind of applications. So we understand the traditional way of handling also. Once we understood the traditional way of handling, now we are looking at convolution neural network, which is also all about dealing with videos and images. But then here it is all about implementing deep learning algorithms. Here you do image processing, which is very different than building prediction models, building cancer prediction models, predicting whether a patient has COVID-19 or not by looking at the pneumonia, lung images, so on and so forth. Those fall under convolution neural network. And any competition that you see nowadays, people are dealing only with videos and images to a great extent. Why? Because dealing with the structured data is a solved problem. When I say it is a solved problem, people know how to solve it. Then why do they need you, right? For the competitions, crowdsourcing. So the world started moving on. They are now working on images and videos and images, while the research is going on 3D images. That is out of scope for us. That's part of our mainstream training, but not here because that needs some other additional knowledge, etc. And of course, overnight you cannot become AI experts. It will take a lot of practice. Hence, what are we doing? All these recorded videos are given to you for the lifetime as part of your YouTube channel. So watch that and type it. Initially, you might feel that, oh my God, why do I need to type it? Why can't these people just share the code? We can as well do that. But the only thing is, you will not learn anything. Okay, so we want learning also to happen parallelly. That is what you do with your students, if I'm not mistaken. You give them assignments, you conduct exams, right? You don't make their life spoon feeding, right? You will not say, okay, this is a question paper, exactly the same thing I'm going to ask you in the main exam. You don't do that. Right? Same. Now, you get into the shoes of students for a while, yeah, and experience that. Not that we cannot share, we shouldn't share. If we are sharing it in the videos, the code, I don't think anything else is going to stop us from sharing the code as is, but we just want to reinforce the learning part. Okay. And when we started off with, CNN part, what we have done is we have first taken a toy example of MNIST dataset and we solved it. Then what did we do? We have taken a tiny dataset, a very small dataset of cats and dogs. Then what did we do? Since it's a very tiny data set, when we built our model, okay, we built a plain vanilla flavor, then your model was overfitting. Since the model was overfitting, what we had to do is we had to resort to data augmentation, which is a regularization technique. So you need to apply regularization technique, and then we have applied augmentation. And data augmentation is a technique that we use heavily when it comes to dealing with images. Okay. Once we have done data augmentation, suddenly we found that accuracy was good. The model wasn't overfitting. Then there is another challenge. Fine, but accuracy was still low. Okay, since accuracy was low, we again had to take a step back to understand on Why is accuracy low? What can we do? Okay, and then we will be working on improving the accuracy further. So look at how we are traversing. First on a toy example, then we have taken a small data set. If you have large data set, anyone can solve it, no problem. But if you have a small data set, your model will overfit. Okay, since the model was overfitting, we wanted to overcome that problem using regularization technique. And we have used two things, by the way. We have used dropout and we used data augmentation. Both of these were used and accuracy was fine. So let me go here and oops, did I close that? I think yes. So let me open Anaconda and let me launch Jupyter. It's launching. Yep. So I will open Spider here. Okay. Here is a CNN complete code. So this is how we traversed. We imported the layers. Okay, we defined the model. We have taken MNIST data set. We have done the data pre-processing in the previous session. You watch the previous recorded video because it's explained in a very detailed way on why we do each of these steps. And then we ran the model. Then we switched gears and then we got into getting this data. Cats and dogs. We can print the data and we define the model. And when you define the model, if you observe here, conf pool, conf pool, conf pool, conf pool layer, and then we flattened it and then we connect it to dense layer. Okay, there is no dropout there. Okay, we did, sorry. Okay, we did not use any of the dropout there. Then you compile your model, then you do some amount of, you build the model and you look at the accuracy, it was clearly overfitting. So we resorted to data augmentation. And once you do data augmentation, you can build your model. So here, if you observe carefully, we are doing this dropout. Okay, we have done dropout. So let me apply this data augmentation here. Hmm. Image generator, where was that? Okay, done. So I will rerun it here. This is what we have done. Oh my God. Sorry, yesterday we have run all these, so it wasn't throwing error because all these packages were installed. We have done data augmentation and then we define the model or specify the model. Once you specify the model, you compile the model. Okay, either using this, and then you have image generator, wherein we use data augmentation heavily. And then we ran a model with 30 epochs, if you remember, and it was working wonderfully well. Now, if we were to increase the number of epochs to 100, okay, let us see to what extent. Why? Oops. don't see that. Okay, let me try. It's saying that your model is not able to. Yeah, it's true. Just want to check whether the GPU is getting initialized or not. Wow, wonderful. So this issue arises when your GPU is not able to handle. Okay, yesterday it worked, today it is not working. Reasons could be multiple. Reasons could be the version mismatch. Okay, so what I should, as part of this, you'll also learn about debugging and all that. Um, so what I shall do is we need to now check which version of TensorFlow is actually working. So when we say import TensorFlow as TF, and if I say print TF dot version, it's 2. Version 2 is pretty stable and it should ideally work. Okay, but since it is not working, what I can also try here is that I can just try import just TensorFlow and or let me remove everything and then let me restart the kernel. Sometimes restarting the kernel also helps this issue, and all I can say is get used to this. It won't, it will throw errors, so because it's imported as TensorFlow version 2. If I run this, it will throw error. I'm sure it will, because I haven't imported as a shortcut here. It's TensorFlow. It's true. That means your GPUs are active. So I will run this and see why it is acting a little weird. All these we have run yesterday, so do not worry too much. I just want to see on why fit wasn't working well. Yeah, don't throw error, please. Yeah, it's working. So restarting the kernel has actually solved the problem. And let me see whether GPUs are getting kicked or not. Yep, GPU is active. Wonderful. Since GPU is active, we don't have any problem now. We can proceed further in importing the data and print the data. You can define the model. You can compile the model, but the only thing is we shouldn't be executing the model. Okay. Now let me go after this data augmentation. Then once again, we will define the model, but the only additional thing is dropout. You see the dropout there here in this line. I am moving my arrow there. Yep, done there. Import. Yep, let me import this. Then it should work well now. And we have optimizers. We will compile the model. We specified the model, we compiled the model, and now we need to run the model. When I run the model, sure, it would take a lot of time, but it really makes sense. Yep, GPU is kicked off. 17% of the GPU is being used. For effectively making use of your GPUs, there are again research going on because only 16% is being used. Can I ensure that my model uses maybe 60% of the GPU? And can it complete these epochs faster? Yes, you can. Okay, you need CUDA programming knowledge, etc. And you can do wonders in terms of optimizing your GPU. And yep, 100 epochs would mean it would take a lot of time. By the time it completes that, let me open FreeMind and we shall now look into this convolution neural network part. Okay. Run the model with the available data as is. This is what we have done. In which, what do? You understand the problem, you collect the data, you pre-process. As part of pre-processing, we reshape the data so that all the inputs have the same dimensions. Then you convert the data into float 32 format. Why? Because when you multiply the weights with the inputs, weights will be in float format. Because weights with which you multiply the inputs will be in float 32 format. And then you normalize the weights, normalize the images to the scale of 0 to 1 so that the weights converge faster to the minima. Then you convert the output data into one hot encoding format so that you calculate the loss function, cross entropy, for instance, if you want to calculate that. And there are other loss functions also which exist. If you want to use that, you need your output variable to be in one hot encoding format. Once you are done with this, we specify, define, design the model. Dimension of input layer should be mentioned. This is usually equivalent to the dimension of input image. Then you proceed further with convolution layers. Size of the layer would be 3 by 3, for example. Depth of the output feature map is given using number of filters. So if you have 32 different filters will be applied on your input image, and that's going to capture the various representations. Then you have padding. You use arguments such as valid or same. Valid means no padding. That's the default option. Same means padding to ensure that the output is of same size as input. Then we have dimension of hidden layers, which you need to mention, right? And hidden layers are nothing but your convolution layers only in this case. So let me mention here that these are nothing but convolution layers. Then you include activation layers. Usually, the activation layers that we use would be ReLU, rectified linear unit. Then you proceed further with pooling layer. You can that helps downsample the images. You have max pool, average pool, or N2 L2 pooling. Then you have striding layers. Default value is 1. This is also used to downsample the images. And then you have batch norm, which will actually normalize the weights using z is equal to x minus mean divided by standard deviation formula. Okay, this will also ensure that convergence is faster. So this does two things. It avoids overfitting and is a regularizer, and this will also help converge to the minima faster. Then you'll have your output layer. Output layer typically depends on what is your output variable. If your output variable is continuous, of course, in images you'll not have that, but still, if it's continuous, you'll have a single neuron. Okay. And better, I do one thing. I'm going to explain that here in MLP because it makes sense for everything. So if your output layer is continuous, then you use different loss functions, loss, cost functions, which you use happens to be this mean error, mean squared error, same thing, mean absolute error, a root mean squared error, mean percentage error, mean absolute percentage error, a bunch of those. And these are typically the same things which you use for error function or model evaluation. Same things is what you use. Here, cost function or loss function is used for optimization, reduce the loss. And if your output variable is discrete in two categories, then you can use either one or two. Put here. Here you can have, let me see, okay. Output layer will have a single neuron. Okay, and loss function or cost function would remain the same. If output variable is discrete in two categories, then you can have output layer will have single neuron, or we can also have two neurons. Then same thing, you'll have loss function, cost function. Once again, I think I need to copy this. Loss function or cost function would be binary cross entropy. Okay, and here you evaluate the model using some accuracy metrics. Whatever you use, you can use confusion matrix. Then if your output variable is discrete and if you have more than two categories, then how do you proceed further, right? And how do you proceed further? First of all, output layer will have as many neurons as number of classes to classify. If you have 10, you'll have 10 in that way. Here we use categorical cross entropy. And then you use same confusion matrix also to proceed further. All right. The same logic is applied here also when you evaluate the model. So you define the model, then you compile the model by specifying the optimizer. You specify the loss to be optimized and what metric do you or will you use to evaluate the model. Then you fit the model within which you give your training data inputs, output, number of epochs, batch size, validation data, and then you evaluate the model on test data. Then you build a practical CNN model wherein you build the model with the available data as is. You look at the accuracy. You run the model with available data by performing data augmentation. You look at the accuracy and you proceed further. It's 33rd epoch still going on. Okay. So I think we should proceed further with the next discussion. And once that is done, I will come back and we will discuss more. Okay. So at this point of time, I would be explaining you about a concept called as pre-trained network. So here we have pre-trained network, but it warrants a separate discussion altogether. Pre-trained network is an amazing concept because not many of us have a lot of GPU compute. If we have too much of compute, then it works well. But we do not have so much of compute. So how are we going to handle in real world, especially if you're doing PhD or any of your students are doing PhD, or if any of your students are interested in doing some research, they probably will be handicapped in terms of having the required compute. They'll not have powerful GPUs, etc. Even if you use Google Cloud or Amazon Cloud or Azure or IBM Watson for that case, the kind of speed that we need and the kind of experiments that we perform would mean we'll run into thousands of dollars. And even for that case, I am a chief data scientist on 4 companies, right? So whenever a small medium enterprise wants to try out these kind of experiments, I suggest them to go with pre-trained models. Okay, so pre-trained model means models which are already trained on previous, uh, you know, some other business problems. And the classic thing which people use is those neural networks which have won the ImageNet competition. And as you know about ImageNet, if I go here, ImageNet was a competition wherein actually all the images were hand annotated. Manually, people were sitting down, looking at an image and giving name to each and every image. There were 14 million images and 20,000 categories. Means like cat, dog, building, car, bus, right? Humans. In this way, there were 20,000 categories. Balloon, strawberry, many things were there. For this specific competition, which was called as ImageNet Large Scale Vision Recognition Challenge, these folks have given away 1.4 million images. That in itself is a huge data set. And on top of this, if you do data augmentation, the count would just explode. So 1.4 million images. These were your inputs. When it comes to outputs, there were 1,000 categories. 1,000 categories and 1.5 million images. So we had 1,000 non-overlapping classes, unique classes, categories, whatever you want to call that. Then, for the first time, AlexNet won the first place. I mean, first place in the sense they use neural network algorithms for the first time ever in this competition. And AlexNet, as I've told you previously and showed you, follows a different architecture. So for one whole year, they were practicing and practicing and practicing, and finally they could, solve this. Where is it? I think the architecture is here. If the architecture is not here, it should be there in either practical issues or challenges. Let me pull out. Hmm. Oh, was it here by any chance? Let's see. Yeah, I think here. And also in CNN, I think that was given clearly. The architecture, I think it's better to go here and go to this AlexNet architecture. This is just a neural network architecture. Okay. For example, you might ask me, hey, how did you decide that 32 should be there of size 3 by 3? How did you decide that activation layer should have ReLU activation function, max pool, all these? Randomly, you need to experiment. There is no silver bullet wherein I say use these settings and you get the output which is of best accuracy. No, not just me, even God cannot say if you believe, right? So we will make use of some architecture which people have experimented for years together. And since this architecture, AlexNet, has won the first place, you can actually just take this architecture and use it as is. Use this as is. All these values, dropout, data augmentation. If you use it as is, you need not worry about how many convolution layers you need, how many filters you need, what should be the size of the filters, what should be the stride, what should be the pattern. You need not worry because I've already tried and tested and they won the first place. In that way, year after year, different algorithms keep coming into picture, right? So they gave different names such as GoogleNet. People from Google also started participating. Then came, you know, something called as VGG. VGG stands for Visual Geometry Group. Okay, so in that way there were many bunch of pre-trained models which have come in. AlexNet, then I think GoogleNet, then MobileNet, different nets came in, and then you had VGG 16. That 16 different blocks. Okay, we'll discuss about those blocks also, blocks of layers. And then VGG 19, then ResNet, residual network. Then people came up with Inception. Then people came up with Inception, ResNet. Then Exception. All these are the models which are built on 1.4 million images. and output had 1,000 classes. And all these models, architectures have won the first place on the entire planet. After doing research for all these years, they came up with this. Hence, what people do is, if they feel that, hey, we don't have the time and money and energy to do such exhaustive research for 1 year, because customer would not wait for so much time. Customer would say, I need the solution in the next 1 month or in the next 2 months. Okay. So speed is important here, unless you are into research. And hence, we can use pre-trained models. But the question is, if I built a model on, say, cats, dogs, tigers, so on and so forth, humans, okay, vehicles, etc., then can I use this model? This is called as, if you already built the model, it's called as pre-trained model. This pre-trained model has two things: the architecture. When I say architecture, I'm speaking about this. I'm speaking about these things when I say architecture. Okay. So you have an architecture, you need to define that. So this architecture, on what layers should we have, what activation function should we have, what should be the size of the input image, all those things would be part of your architecture. And alongside that, it will also have weights. So when you have a network will learn what weights, all the weights. All those weights are also captured. These weights will extract the features from your data. Now the question to you all is, can I use this pre-trained model on cancer prediction, for cancer prediction? And say for cancer prediction, you have X-ray images. If you have X-ray images, etc., and what do you do in that case? Is a question. So okay, let me put a poll question and then I'm going to answer this. So here, poll question is, can I use a model trained on cats and dogs for cancer prediction? Yes or a no? Think and answer, because I won't obviously ask obvious questions, right? So please think and answer. Okay. A few of y'all are saying yes, a few of y'all are saying no. Okay. All right. So roughly 50% of y'all are saying yes. Roughly another 50% of y'all are saying no. So I'll give you solution to this. So here, when you build your network, if this is your input layer, and say these are your convolution layers, 2D, because image is in 2D format. Then again, say you have your 2D layers, so on and so forth. And then finally, you have the output on whether the image is cancer or not, whether the tumor has cancer or not. Okay, tumor is cancerous or not. My bad. Excuse me for my communication mistakes there. So this is your output. Initial layers of your network will capture low level information. Initial layers will capture what information? Low level information, low level features. When I say low level features, if you take an image, for example, it will capture each and every pixel value. Each and every pixel value. So every pixel is important. Maybe you'll capture the intensity values, pixel intensity values. Maybe you'll capture the edges. Maybe you'll capture the texture. Maybe you'll capture the blob, motif. All these are the various features that you can capture. So the initial layers will capture that. If I take a cat, okay, if I take a cat, and if I take cancer image, which will have some kind of shape, yeah, some kind of shape. This cat also has edges. These tumors also will have edges. So the initial layers which are capturing edges here will also capture the edges if you give any image whatsoever. So I can use the initial layer which is capturing the edges on the cancer image also. Then the mid-level features or middle layers will capture mid-level features. Mid-level features means it could be blobs. Blobs means circles, basically. Circles, right? Some kind of circles. Here also in tumor, you'll have circular shapes. So I can use the mid-level features even for the cancer image. Same layer, which was trained on cats and dogs, can also be used on cancer. The and then you'll have the high-level features. High-level features means identifying the entire face of a cat. So I don't need the entire image. I mean, all these other bordering pixels, all these pixels are irrelevant. I want only this portion. Hence, you do max pool, right? We do max pool to keep reducing the size of the image. Why? Because initially I need all the pixels. Later on, I need to have only smaller portion. Where we don't need such lengthy image throughout. Okay. So high level features are captured like its cat, face of a human, etc. These high level features certainly cannot be used on cancer images. You don't want to use that. But at least until the mid level features, I can reuse the model. And this is called as making use of pre-trained model. Okay, because initial layers and mid features, mid layers, middle layers will capture features which are common in any image on the planet. You take any image on the planet, it will capture. All right. So this is very, very important. Okay. So you can reuse, and that is what the world is doing. Now, next, feature extraction. What do you mean by feature extraction? Feature extraction is all about learning the features from your images. So all you will do is you'll use your pre-trained model. You'll use the same architecture and you'll use the weights of that pre-trained model. Means already it is trained on some other data set. You're going to use that architecture and those weights to extract features from the new data. So when you have new data, you extract the features. Okay. These features that you learn, all the features are like inputs. You're learning the inputs. So you have the input, you have all the con, max, pull in that way, all these layers. And whatever features you learn, and the last layers will learn exactly features pertaining to the input image. Hence, you'll get rid of these and you'll use only features until here. Features means all the inputs. Features, learning features means learning weights. So you extract all those new features, use these features and supply all these features to the model that you want to build, a new classifier. You'll just use your dense layer and the final output layer, and then you get the output. Okay. And in the previous example, we have already seen that when it comes to convolution neural networks, there are two parts. One is you have the conv layer, pool layer, conv layer, pool layer, and finally you have the dense layer. This is how it was, if you remember. Let me do this. The initial layers had conv, pool, then conv, pool. You had such layers, and then finally what did we do? We connected that to a dense network or a fully connected network, or it's called as fully connected classifier or dense classifier, which used to classify and give us a final output. Okay. The first part, that is this part, where you have conv pool is called as convolutional base. This part is called as convolutional base. Feature extraction consists of taking this convolution base of a previously trained model, and that's a pre-trained model. Take this convolution base, run your new images through that so that all the features are captured. And then what do? You, instead of having this dense classifier, you have your own classifier. Okay. So we are only trying to reuse this part. We are going to reuse only the convolutional base. Could you also use dense layer to, you know, can you use or can you reuse your dense layer? Sure you can, but you don't want to do because Your model was pre-trained on cats and dogs and tigers and cars and buses and buildings, etc. And now you are testing it on a different data set altogether, maybe cancer data set. So it really doesn't make sense for having to have your dense network, or for that case, even the last convolution base, exclude that and try out, right? And the main reason here is this convolutional base that you're going to have will learn generic features. Since it's going to learn generic features, you will try to reuse that. And these features, or the dense network, is going to capture specific, also your high, I mean, your, you know, finer layers capture usually specific features. If they are specific, you do not want to reuse that. Okay, so we will again continue that when we do practically. I think the 100th epoch is running. Let's run this 100th epoch, and then good that we have finally arrived at the 100th epoch. Wonderful. So 82% is the accuracy. Now what I will do is here we will save this model. Save, done. Save it, keep it handy. Now what we are doing is we are doing matplotlib as PLT. We are importing that. If you give, instead of history, if you term this as ABC, ABC dot history will have accuracy, it will have validation accuracy, it will have loss and validation loss. So you are taking all those four values for all the 100 epochs and you're storing it in these objects: accuracy, validation accuracy, loss, and validation loss, in these four objects. Then what are we doing? We are saying I want to print numbers in the range of 1 to length of accuracy plus 1. And within Python, indexing starts from 0. So 0, 1, 2, 3. If you have 100, it will go all the way until 99. So 1, 2, 3, 4, 100 would be there. 1, 2, 3, 4. But if you say 1 until length of accuracy is 100, if you say 1 to 100, it will take 0 until 99 and stop. Or not even 99, it will stop before the final value. If you say plus 1, you're just including one more number so that you have all the 100 epochs. Okay, that's the reason why we have. And we are saying epochs. Now if I say plt.plot, always when you plot, right, it's all about x comma y. What do you want to have on your x-axis and what you want to have on your y-axis. On x-axis you want all the epochs, and on y-axis you want all the accuracy values to be plotted, and you want all those points, accuracy points. Epoch 1, what was accuracy? Epoch 2, what was accuracy? All those you want in blue color circles, and you want to give a label to that as training accuracy. Then you will also plot same epochs on x-axis. On y-axis you want validation accuracy, so that you compare training and validation accuracy. This you want in blue color line. You want to give a label for validation accuracy. Then overall title should be training and validation accuracy. You want legend. Legend means you'll get a box like that. It will say that, okay, blue color circles are training accuracies, blue color lines are validation accuracy. And then you want to see the figure. Let's run this. Wow, wonderful, isn't it? The accuracy values have kept on increasing both for training and validation accuracy. They are not overfitting. That's a good part. I think it's still increasing, so you can increase this to maybe 500 epochs and then try out once again. Okay. You can either do this or also you can plot the loss, training loss and validation loss. Here we go, training and validation loss. So either you can use accuracy or loss. Okay. So this is how we could build a good model, right? Simple. We have just done data augmentation and job done. One second. Sorry. I think it's big time. A few of y'all are asking for break. Okay, let's do one thing. It's 11:36. Let's be back by maybe 11:46. 10 minutes break, and then we will move further and complete the CNN story. And people who are wanting to quickly work on textual data, just hold on. We will get there. 10 minutes break and then come back, please. All right. So let us get started. Hmm. Experiment, Sandhya. Experiment. Okay. Then Venkat Subbarao has a question for diversity of data. We go for data augmentation. How can we use here? That is auto ML. It's out of scope. It will automatically do it. Auto ML is a different subject in its own. Could you give one real-time example? These are all real-time examples only. Okay, these are all real-time examples. These are not textbook examples. Taking an image, classifying your image as a cat or a dog, right? Predicting whether an image has cancer or not, cancer prediction model, object detection models. If you have a driverless car and if the driverless car is going on the road, okay, then suddenly there is a cat or a dog which runs across the road, then your driverless car should identify that. Hey, it's a dog, and apply brakes. Okay, right, Ravindra? Okay. Okay, no worries. We just put the on the sticky note, we don't put anything else. We just put the YouTube link. That's it. You need not look at the sticky note as part of the training. Okay. Yeah. What else? Yeah, this is feature selection, feature extraction only. Feature selection in neural network happens automatically, Kishore. Automatically it happens. Okay. Feature extraction is something which we are doing now. Weights that you learn is nothing but feature extraction only. Okay, don't think about your traditional shallow machine learning algorithms here, because in deep learning models, automatically features are extracted. Making sense, Kishore? Automatically features are extracted. And what do you mean by feature extraction in neural network? Weights, which your model learns. Okay, let us proceed further. Now, how many convolution bases do you want to use? Which one do I use? How do I experiment? The one key thing that I request you all to take away as part of the training is experimentation. Okay, and auto AI, auto ML, see, those things are out of scope actually. I can show you here. We cannot get into that depth because there are different people from different backgrounds attending. We want to take everyone along with us. Okay, so we have this auto AI. Do you see all these techniques? GCP, Azure, AWS, auto ML systems, auto ML methods, right? And not just that, we are also even more futuristic in terms of bringing in your to you explainable AI concepts also. Yeah. So hope that answers you. There are too many things to be covered in 60 hours. All right. So now we are discussing on how do we use pre-trained models. And within Keras applications, you have VGG16, VGG16 network, okay, which was built on ImageNet. We are going to load that model, VGG16, and we are going to reuse that model here. And when you go to this Keras applications, you'll have a lot of pre-trained models, such as exception. You have inception v3, We have then ResNet 50, then VGG 16, VGG 19, MobileNet. These are all the various pre-trained models which come to you as part of Kera's applications module. You just need to import that and reuse that. Okay. Very clearly, you're saying that you want VGG 16, you want the weights which were trained on ImageNet. You're saying that your model should initialize the model right from here. So what does that mean? Say you have your inputs. You'll have convolution, 5 convolution bases. Okay, when it comes to your VGG 16, there'll be 5. What are those? You'll have input, you'll have conv, pool. This is called as one block. Okay, let me first complete all this. Okay, and then you'll have again conv pool, conv layer, pooling layer. This is the second block. Then you'll have conv pool. This is another block. Then you'll have conv pool. Yeah. And then again you'll have conv pool. Okay. And then you're saying include underscore top equal to false. So after this, do you know what? You'll have dense, and then you'll have what? 3, 3, 6, 10, 14, 18. How many com layers did I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 16. Yeah, yeah. You'll have 3 layers here. 2 fully connected networks and then the output layer. But you're saying include top equal to false. So this portion would not be included when you say include top equal to false. And this is your block 1. This is your block 2, block 3, block 4, and then you have your block 5. All these 5 blocks put together, is called as convolution base. Convolutional base. Okay. So the moment you say include underscore top equal to false, this fully connected dense network will be gone. Dense layer or fully connected network is gone. You will not have it. And then you have all these blocks. Conv pool, conv pool, conv pool, conv pool, conv pool, fully connected, and the output layer. This is how it will be. And what happens here is you have to initialize the weights. How are the weights initialized? Randomly. And you'll have this error surface. Randomly weights are initialized. You keep updating the weights to get to the bottom. But here the advantage is whatever weights you get here, whatever weights you get here, while you pass your images through, all the features are learned, and these weights are taken, and from here your weights are whatever are the weights, it gets initialized from there, and then it does the same thing back prop, keep updating the weights, keep updating the weights until you get to the bottom. So include underscore top here refers to including or not your densely connected classifier. Should I include this or should I not include this is something that is used. By default, the densely connected classifier corresponds to 1,000 classes of ImageNet. You have, VGG16 was built on ImageNet, you'll have 1,000 classes here. But here we are dealing with only cats and dogs. Okay. And hence we need two. And that is another reason we don't want to do this. Hence we are saying include top equal to false. Then you have your shape, wherein you're ensuring that all of your images are of this shape, 150 by 150 by 3. 3 means color images. Okay, now I'll minimize this and let me run this. When you do convolution based summary, look at that. There are approximately 14 million weights that your model is going to learn. And the final output will be 4 by 4 by 512. This is the final feature that your model learns. This is the final feature that you need to put on top of your densely connected classifier. There are two ways to do it. Now, at this stage, there are two ways to proceed further. One way is take your entire cats and dogs images, pass it through this network. Finally, you will get these weights. Take the output, save it on your hard disk. And then use this data as is and supply it to your standalone, like treat that as a multi-layered perceptron. So you saved all these weights in the disk. Until now you have run that CNN model. Now you are supplying that to say your MLP or densely connected classifier. This solution is fast and cheap because you need not train your model through all these weights. Weights are there, it's just mathematical calculation quickly. And then you have all the weights. Take those weights, pass it through your densely connected network. Quickly you complete your model. But the disadvantage is, okay, you cannot perform data augmentation. When you apply such a technique wherein you save these and separately supply, you cannot perform data augmentation. Okay. Hence, what people also do is they extend the model you have. Until here you have all these convolution bases. You just extend the model by adding our own dense layers on top of this. And let the whole thing run at one go. You cannot interrupt it and then run it separately. If you're doing data augmentation, you have to run it completely. Okay, this will allow data augmentation to be performed because every image will go through your convolution base every time. Okay, but this is slightly, tedious task. It will take slightly more time. Okay, so I will show you how it is done. From here on, I would be a little fast in terms of walking you guys through each line of code, because same thing is going to be repeated. I'm importing the required data sets, image data generator. You're running through, you're doing that pre-processing. You're extracting the features, right? And then you're defining your model, and then you're going to fit your model. Same thing, there is no change. You're doing just additional data augmentation, and then you're running your model. And here, if you observe, what are we doing? We are adding only a single dense layer or two dense layers. One is this, another is the final output layer. And since you have your final output layer, it's cats and dogs. So you'll have a single neuron, and activation would be sigmoid. See how fast it is done. Within 1 minute, it is done. And look at the amazing part of accuracy. Earlier, it was 79, if you remember. Now it is 91. The same code I'm going to run, and then I'm going to show you how the accuracy would be. Look at how smooth it is, right? You have your training and validation accuracy, bang on, right? You could just increase the accuracy. And we achieved an accuracy of what? Amazing 90%. This is what did we do here? We just extracted the data, okay, and we have supplied that as a separate input to your standalone classifier. We extracted all the features using VGG16, and we have taken those features or weights, and then we have supplied them separately to your model, standalone model. But then, if I were to add the dense layer, okay, on top of the convolution base, if I take the convolution base, how many weights your model was learning? Approximately 14 million. If I take those weights, and then now if I supply the dense network, what do you think will happen? The number of parameters that you're going to learn will just get exploded. Okay, two things. Once again, I'll repeat. You take your images, pass it through VGG16 on use only conv base. And then you finally get an output. Okay, output will be nothing but weights. How many weights were there? 14 million weights. Take all those weights and supply it to your fully connected network or dense network. And you get your output. Wonderful. But here, what is the disadvantage? Disadvantage is that you cannot perform any data augmentation because you're breaking the chain here and then taking the weights and supplying separately here for this reason. And what is another way? Take your images and to this VGG convolution base, add your dense network and make it one big network. Remove whatever dense network was there and add your specific dense network and proceed further. When you do this, the advantage is that you can also do data augmentation. But the disadvantage is these many weights, you are taking it forward again from here. So I can show you the summary. 16 million weights. Okay, now I can say what are the number of weights before freezing the convolution base. What is the length of the trainable basis? 30. After you freeze the convolution base, there are only 4. When you train the model, it is very important that you freeze a layer. Okay, otherwise, what will happen is if you don't freeze it, if you don't set it as dot trainable equal to false, inputs will be taken and you have your VGG16 convolution base, your model will retrain all the weights again. If you say this convolution base, I don't want to train it, it will take the image, pass through this as is, and whatever your dense network is there, it will pass through. But then here, whatever is here, you just, those many weights have to pass through here. Those many weights have to pass to the subsequent layers. If you break it here and take it newly, then it's as good as training only on these weights for the new model. But here, since you're continuing whatever weights you learned here, you continue with those many weights and move forward. That is the difference. Okay. So, and also, as I've told you, the advantages, you can also perform data augmentation. So the same data augmentation steps that we discussed yesterday, the same thing is applied, and you compile the model and you run the model. Just see what happens. It would be slightly time consuming. It won't be as simple as, as fast as what we have done earlier. What might be the reason? The reason is you have a lot of weights. All the weights have to be again taken forward in the calculation. Let's see how much time it's going to take for first epoch. Usually takes a touch more amount of time, and from the second epoch onwards it will take slightly less time. I'm sure about that, but let's see. For 2 to 3 epochs, and since it's 30 epochs, we will not wait for this to complete. We'll proceed further with the next set of explanation. It's running, it's taking a while. So a lot of you all were asking me on practical examples, practically. All these are practical. Maybe you're not able to relate. So let me explain a few things. So here, when you have life sciences healthcare analytics, we built a cancer prediction model, triple negative breast cancer. Okay. Or I can do one thing. I will open the email ID. I happen to be a chief data scientist on one firm. I'll just stop the screen share and then I'll proceed further. Hope you all are getting responses from our team. Don't send me private message because I'll be training, right? So I don't look at it. But we have a team who is actually monitoring your questions and they'll be responding. That's a kind request. Nagasai Babu, you also can do that. Yep, amazing accuracy, Pawan. Some lines are too long that their ends are not visible in the video. That would make it difficult. Good for practice. Okay, sure. I'll look into that. No worries, Surya. If we add one more dense layer so that it may increase it. It may increase, but it might also overfit Sambasivarao. It might overfit your model. If the weight is increased every time, it won't be a problem to our image or it will gain advantage to accuracy. You don't increase your weight, you update your weight. Updating the weights could be reducing or increasing your weights. Okay. Hope I answered Dhanush your question also. Sure, Surya. I understand. Zooming is not helping, right? I'll look into that. So just give me a minute while I pull out the document which might be an area of interest for you. What we have done, what work we have done, I'll just explore. So let me share my screen and I'm going to show you this interesting bit of it. It will be updated. Each time it will be updated. Now I'm sure it's updated. If the mind map is not updated, I will get it updated right away. It should be updated. I just asked our team. They should have done by now. Let me see. Yep, it's updated. Okay. So you have the updated one. Right. In this way, we will frequently keep updating. No worries at all. Experimentation, Ravindra. Experiment. That's it. One single solution. Vijay, using Google Colab, there is nothing to teach actually here. Let me show you. This is Google Colab, my dear friends, while that algorithm runs. If you open Google Colab, okay, you can say you want a new notebook. It will open a new notebook for you, which is nothing but Python. You just need to run it. It's taking a while. Yeah. If I type 1 plus 1 and enter and click on run here, it will give you the output as 2. Uh, if it's taking too much of time, that means you're using a typical CPU machine over there. I'll show you how to switch to a GPU or a TPU, tensor processing unit. See, it's saying it's 2. So I'll go to runtime. I will say change runtime type. Okay, here you can choose whatever you want. Say you want a GPU, you save it. And you add the next line here. You say 1 plus 1 and click on run. We'll say 2. See, it was very fast, right? You add another line of code. You copy this here, whatever code you have. And when I come here, if you paste it here and click on run, come on, shouldn't take so much time. Maybe for the first time, it's getting those libraries, it's taking a while. So here is output. Okay, that's it, friend. That's it. You just click on code, you run the next line of code. That's it. Only thing that you need to bear in mind is if you are using this by upgrading your version, then please click on manage sessions and click on terminate. Otherwise, if you don't click on terminate, it is going to cost you. 88 GB of RAM is used and 0.12 GB of GPU is used. If you do not terminate in this way, it Google is going to continue charging it, and you have to give your credit card if you want to upgrade. And automatically money will get deducted. Please bear that in mind. A lot of people complain to us saying that this is what is happening. Okay, then Sambasiva Rao, you have to do a Google search. I already explained you what pre-trained models are there, right? But if you want everything which is there, I explained. You have to probably relook at the recorded video, or you can do a Google search. We are dropping a layer during training phase by mentioning it as false encode. Yes, we are dropping it. Okay. Now I'm assuming you want to know about this practical application. So let's get into this. So this is all about taking the radiology images and pathology images and then doing some analytics. So what in this particular project, what we have done is when doctor and a patient when they are going to have conversation, that conversation is recorded on a piece of paper, right? That's called as prescription form. This prescription form is automatically digitized. We scan this document, we do vertical projection and horizontal projection, and we take the data and automatically place it on the database. One thing. Second, we take radiology images and you do CNN, get the interesting insights, radiology insights, and then use pathology images and get the interesting insights. This is all image processing wherein you use CNN, right? Here also you use CNN. And then you come up with a consolidated report. Alongside checking whether your radiology pathology images are cancerous or not, right, malignant or benign, we also give a report saying that this cancer seems to be spreading at a rapid pace and treatment should be given for 8 months. There should be a surgical removal of the tumor, or should there be chemotherapy provided. All those kind of details are consolidated and then shared with oncologist. So for coming up with this textual information, we have made use of recurrent neural networks. This we are going to discuss next week about RNN networks. Okay, so you have CNN and RNN in combination, you have an output. All right, then you take an input. This is a breast cancer, breast mammography image. You take that, segment it, get to the region of interest. You use your algorithm, do a transfer learning or pre-trained models mean the same. Then you automatically get the data. So we have not just used a CNN model. Okay. We have also used our traditional models by using all the filters that we have learned. We have learned a lot of filters, right? Why? Because of these reasons. And look at that. Test accuracy, it was not CNN which was giving us good accuracy. What was giving us good accuracy? Gradient boosting classifier. Because the number of images were very less. Then what did we do? We have done data augmentation. And then accuracies were awesome. This is called as a whole slide image, pathology image. You take that image. Okay. This one image was 1.5 GB in size. You cannot open this image in your regular computer. You need specialized softwares for that. And then we extracted all the tiles of image. We got the region of interest. After getting each and every tile, we analyzed each and every tile, and then we have done a pre-trained model on that. And finally, we could get certain accuracies. On different dimensions of images, we have run it. Sobel filter, color map, various other things we have used. And this is the team we have used radiologist. I happen to be a chief data scientist there. This is the team, and then microcalcification identification, right? It supports radiologists and pathologists and oncologists. A lot of benefits were there. We have done analysis on what are the Siemens system that we have, what CAD systems that do we have, how is our system going to be different, Bairat's calculation, so on and so forth. Okay, and I think this is not needed. Okay, hope that answers to a great extent. Yeah, next. Okay, once again, please put don't do a private chat, do a public chat, because people might feel that I'm again and again posting. the mind map, but you're asking, right? Suparna, you're asking, so I'm posting it. I'm unable to see the sticky notes message above my chat, but that's okay, Suresh. There is nothing in that. You can ignore it. Then is it possible to apply deep learning for textual data instead of images for classification of huge categorical classes? Okay. So after CNN, we are going to learn about RNN, recurrent neural network, within which you'll have long short-term memory and you'll have GRUs, gated recurrent units. Okay. And RNN is all about dealing with your textual data, sequential data, time series data also can be used here. Okay. We will learn about this, but we will learn about this in next week. Right, Venkata Srinivas Rao? Is that making sense? Any IoT integration? Yeah, IoT integrations happen. We have different teams working on that. Okay, we completed our 30 epochs, and now after running those 30 epochs, what we can do is we can actually uh, you know do I mean, you can increase the number of epochs because if you feel that the accuracy is increasing, you can also increase the number of epochs, but it's fairly good. Accuracy here and training and validation has converged to a great extent. 88 and 90 almost same. So no room and no scope for overfitting. Having said that, now we are going to discuss about fine tuning the model. I'll get here, but then I can also, I think, uh, so let me see until where we have run it. Yeah, I think we have run it until here. Now what we can do is we can just run this same thing. We are going to visualize the data. And yeah, you have the training accuracy and validation accuracy. Both are increasing parallel, right? Loss is decreasing. Either you can look at loss or you can look at accuracy, doesn't matter. Now what we will do is, as I've told you, this VGG16 has different blocks. Okay, you'll have convolution block 1, wherein you'll have conv max pool. Then you'll have another base conv max pool. This is called as block 2. Then again you'll have third block, which is conv 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 max pool. Then you'll have another block here, which is again conv max pool, block 4. Then you'll have a fifth block here, conv max pool. And then you'll have a dense network here, which is flatten and dense and dense. Flatten, dense, dense. Okay. So you have block 1, block 2, block 3, block 4, block 5, and then you have this fully connected classifier. Fully connected classifier. So what we will do is we will actually stop until here this time, and then we will fine tune this block. So this is another very widely used technique. Fine tuning is a very widely used technique. It is a complementary to your feature extraction. What fine tuning does is it is going to unfreeze. It is going to unfreeze your topmost layer. The final layers are called as topmost layers. You unfreeze that. And then what do? You jointly train both this final layer. You put your own layer, or you'll just unfreeze this, and you'll train this and this both. It slightly adjusts so that, as I've told you, the higher layers will capture more specific features pertaining to your images. Right? It captures specific features pertaining to your images, these layers. Hence, if you unfreeze and also train it, this is going to learn better features. It's going to learn better things. So you unfreeze these layers and jointly train these two. This is what we are going to do. Okay, so once again, to show you, in the earlier layers, I'll come back to this. First, let me run this VGG16 and let me show you the summary of that so that you get a sense on what features we have. Okay, there we go. So in this, if you look at the output in VGG16, con pool, this is your block 1, this is your block 2, block 3, block 4, and block 5, and then you have your fully connected network. Why are you not able to see a fully connected network? Because we are saying include underscore top is false. If you say is equal to true, even you will see those things also. Now our idea is to take this block 5 and unfreeze it. So you're going to supply your data, and your data will learn from these 4 blocks, and it will learn the features. Learning the features means extracting the features. Extracting the features means feature engineering. Means nothing but you learn the weights. All mean the same. Okay, you take the weights, extract all these features, or learning representations also mean the same. You learn all these features, extract the representations using the weights that we already have. Once you extract the features here, you pass those through your model and let your model again learn the features. Okay, since the initial layers are more generic, they are also called as reusable features. Okay, reusable features. Whereas the higher layers are going to capture more specialized features. So it is always good to fine tune these layers. Okay, it is always good to fine tune the layers here. Okay, when you do this, you learn better features, right? You learn better features specific to your problem that you're trying to solve. Okay, so I'll go here and then show you that. So that is exactly what we are doing. We are looking at convolution based summary, and we are saying base.trainable is true, you want to train them, you don't want to freeze. But then all you're saying is if the layer is equal to block 5, here block 5 convolution 1, right? If you have that, then set trainable equal to true, otherwise say trainable equal to false. That's it. That's the only difference that is needed. And then you can retrain your model once again. So I'll run this and we will fit the model. This time for the number of epochs, how many do I give? Because it's going to take crazy amount of time, I think. Okay, let me run it for at least 30 and let's see what happens. Okay. If it's going to take crazy amount of time, that's okay. It's an hour. We will take anyways 10 minutes break. So I'll just wait and see how much time it's going to take per epoch. For y'all, don't test it on your CPUs. It won't run. You need to have a GPU machine. Even better will be to work on a distributed environment, big data environment, Hadoop, right? And we have done a lot of projects for Korean Airlines, Avianca Airlines. We have implemented for Government of Malaysia, Sarawak, which is a state in Malaysia. We have implemented for the government sector, and there is a specific bank in Malaysia. For them also, we have embarked on this journey, right? So amazing things is what we have done in space of, I can tell you that while this happens, industrial IoT sensors plus cloud plus big data plus data science and AI and deep learning plus cyber security. This is our strength. When we implement our projects, like we are doing it for Coca-Cola, okay, we have done it for Korean Airlines, we have done it for Avianca, which is Latin American airline firm, for Yatra, Make My Trip Yatra, right? Yatra is one of our clients. Tata Trust is one of our clients. And a lot of overseas clients is what we have. We keep doing projects for them. These names you understand, so I've told you. A lot of other clients are even more prestigious. We keep doing all of these things. Okay. So application wise, a lot of domain knowledge is needed. And for Korean Airlines, when we have done, there were 12 different models that we built on distributed environment. They had crazy amount of data about their cargo. And we were expected to use deep learning algorithms to build forecasting models. And we have used long short-term memory. We have used BERT. Now we have XLNet. You have transformers. All these are the advanced techniques that we have now currently. And of course, those are not there in this FDP program, but it's otherwise covered, right? So it's running. Let's take a break. It's 12:35. Let us be back by 12:45, and then we will take this discussion further. Okay, so I'm not even speaking, Krishnaveni. How will you get an audio? Okay, I just unmuted to speak. How can we say a model is convergence? If your training and testing accuracy is close to each other, you can say that. Next, weights are vectors, am I correct? If so, how can we treat it as features? Those weights are vectors which will capture the features. Simple. Okay. Next, observations features. Yes, right. How weights are called features? Because in a neural network, weights will capture the features. You don't know which feature it captures, by the way. It's all black box. Line is too big, horizontal, one so that is fine, Anil, no problem. We'll look into that. Feature engineering is dealing about which are the features. Not really, Dr. Sendil. It is much more than what you think. Okay. Feature engineering is feature extraction, feature selection, feature normalization, many things. Yeah. Overlaying GIS on IoT mobile data. Fine. Okay. Shakina. Wonderful. Okay. With only flatten, any other way to connect the. No, you have to flatten and then correct. There is no other way to connect actually, Vishnuvardhan. Can we give a learning guide? Yes, you can, Anil. We are going to look at speech audio processing with ANN models. Yes, we will briefly discuss about that. Yes, we will. About the speech audio processing. And then provide us updated mind map. I think I've been sharing that updated mind map. Fruit detection, OpenCV is better. Yes, OpenCV can be used, Bharati, for fruit detection. Any IoT integration? Yeah, I think that we have discussed all of these. Yeah, wonderful. Next, is there any possibility of giving the certificate as online course rather than FTP? For that, we are supposed to check with AP State Skills Development Corporation, actually, Suresh. We'll check and let you know on that. And then Samasiva Rao says, if you stop running the model before completion, will the weights gained useful for model study? Yes, you can still use it, but it may or may not give you good results. Sri Venkata asks, can we recognize unknown signals using deep learning? Only whatever you learn, you can recognize. This is like humans, okay? Uh, Sri Venkata Sheshu, it is like humans, right? Whatever you teach to a student, they can only solve those kind of problems, right? Like your students, if you take your students as example, you taught them 5 topics. If you test them on those 5 topics, they will do well. But if you're introducing another different topic which you have not trained them on, they will not be able to learn. Right? It is exactly like they'll not be able to answer those. It is exactly like that. Whatever you train, your model is going to learn those. Yeah. Any other questions that we have before I proceed further? Which maybe our team has not replied because we have a team in the back end, they are replying to your questions. If they did not reply any of the questions, please ask. Is it sufficient for running them? Yeah, it can. You can use that, Deepak. How can we say a model is convergence? If your training and test error accuracy is close to each other, Jagadish, we say that a model has converged. Yeah. Um, that's okay. I mean, there is nothing there in the sticky pad, Murthy. There is nothing. We didn't put anything on the sticky pad. Don't worry about that. It's just the YouTube link. That's it. When we give the attendance, we'll put it here and then you can give the attendance. Ravi Mamta, that's a tricky question. No, you'll have to do your assignments. You'll have to do the live projects. You'll have to learn a few more additional concepts for getting a job. Is this good enough for enhancing yourself further? Yes, it is certainly helpful in enhancing yourself further. There is nothing which is there on the sticky note, Chandrasekhar. Let me remove whatever is there. Yeah, there is nothing. No sticky note. Happy? Nothing. When we ask you to give attendance, we will put on the sticky note and also will put on the chat here, and then you can do that. No, there won't be any assignments for this. Dr. Murthy. We won't give any assignments, nothing will be there. It's just a plain training. Okay. We'll give the feedback link in another sometime. How to judge convergence either with iteration count or fastness on result. I didn't get you, Lakshmi Devi. You can decide on whether your model converged or not. Okay. Based on whether your training and test accuracy is close or not, number one. Number two, sometimes in 10 epochs, you might reach the minimum loss. Sometimes you might reach your minima in 1000 epochs. Sometimes you might reach in 10,000 epochs. How fast you're going to reach the bottom depends on various parameters such as what is the learning rate, whether you have normalized your data or not, which optimization function you're using, what is the learning rate of that optimization function that you're using. It depends on various such parameters. Okay, I think I answered all of your questions. Now let's move on. So here we have executed our model and we have the accuracy here and we have the validation accuracy. Now you can just simply put smoothen it a little and then you can view it and then you'll be able to see the results. Okay, it's actually stabilized here, but maybe you can run for 100 epochs, 200 epochs, maybe you'll get better results, who knows, right? Until now it's 90% and 88%, but the way I see it is still increasing, so you can increase it further to 100 epochs and see what happens. Then you have text. Now what you're doing is you're taking your test data and you're saying you want batch size of 20, and then you are now saying I've built a model, it's very good, evaluate my model on the test data by taking 50 images at a time, and you're evaluating your model now on the test data. And then if you look at the test accuracy, it says that the test accuracy is 89%. Okay, this is what we do. And now explainable AI, a little bit of explainable AI is what we can discuss about. Briefly, I will talk about explainable AI. Okay, explainable AI means, say for example, there is a person who has applied for a loan. Okay, and when they apply for the loan, they give you information such as age, gender, educational qualification, the companies that they have worked with, what is their income, so on and so forth, number of dependents and all that. Based on all this, you then say supply this data to a neural network algorithm. And then your neural network algorithm says that there is going to be 80% probability that this person who has applied for the loan, person A, will default on the loan. If you do it in India and based on this, what will you do? Will you approve the loan or reject? You'll obviously say, hey, I'm going to reject the loan. In India, if you do this, there is no one to question. Including South America, now they have come up with GDPR norms similar to European Union. European Union GDPR norms say that this general data protection regulation. According to these norms, there are a lot of norms in this. One of the norms says that if a bank is rejecting the loan Okay. And if this person goes and asks the bank on, hey, dear bank, why did you reject the loan? I see that you have rejected the loan. Give me a reason on why you have rejected the loan. Then the bank cannot say that I don't know. I've run this data through your neural network, and the model says that there is 80% probability that you will default, and hence I've rejected. Then this person can sue you in the court, and you will end up paying huge penalty to this person. So you better be careful when you are approving or rejecting the loan in such nations which are strict on GDPR. Indian government also has uh, tabled this bill in uh, the BJP's first term itself. But then a lot of lobbyists, lot of industrialists have put a lot of spanners, saying that no, we don't want such stringent norms and all that. But then again, their discussion is going on with the industry leaders to ensure that India also brings in such tight norms. Okay, so here, why can't the bank explain you on why they cannot, why did they reject the loan? Because you have used neural network, which is a black box technique. You cannot interpret what those weights are. For example, if you look at linear regression, you'll have an equation like this: beta naught plus beta 1 x1 plus beta, or logistic regression. It will have like this. So you'll have some numbers: 12.1 plus 1.6 into age, right? Minus 1.5 into income. Then you can say that this income is going to negatively impact your chances of repaying the loan. Hence, I've rejected the loan. You can give such an explanation. Of course, that's not a correct explanation because these are all, um, log of coefficient values, and then you use that in another equation to get probability. But that's fine. Not going, not I'm not going to get into the depth of this. But then this kind of interpretation exists, so you can interpret the results. But when you use your neural network will give you a model like this, wherein you'll have weights, some weights 1.6 minus 1.3 into age plus 1.2 into income. Some weights is what you'll get. These weights have no explanation. You cannot do any interpretation by looking at these weights. Hence, it is called as black box technique. Hence, you cannot go back to your customer and you cannot tell to your customer on what are the reasons why people have why they have rejected your loan. Banks cannot give you that explanation. So judiciously you have to use. I mean, just saying that, okay, give me a use case, I'll work on that. Wonderful, you'll work on that. But then is it practically applicable or not to the business? People will ask you these kind of real world questions in interviews. Okay. We should not get confused. If you're assuming that people will only ask you technical questions, that's your myth, right? If I were to hire someone, obviously I need them to understand the business aspects more than the technical aspects, because I want them to build prediction models. I don't want them to write programs and do that, things of that kind, right? On similar lines, when you have images, say you have a face recognition system. If you're building a face recognition system, then say this is a human body, and your algorithm is able to predict you correctly. However, your algorithm is looking at the hands and then predicting that this is a human. Would you rely on this? You don't want to rely, right? You want to rely only if your model is actually looking at the face and classifying that this is a human. But how do you know which part is getting ignited, which part is getting highlighted? We really don't know. Okay, that is your typical neural network. Black box. But then what people are doing is your DARPA, US DARPA, which is from US military, they are working on something called as explainable AI, which will not be completely black box. It will bring in a lot of explainability concepts. Okay. Hence, your cancer prediction models, etc., are famous when you deal with images only in those countries where the regulatory norms are not strict. In those countries where regulatory norms are strict, you cannot just say that, hey, I've used a convolution neural network and it's saying that this particular tumor image is cancerous, right? The tumor in this image is uh, showing signs that it's cancerous, malignant. But explain me why, you have no clue. If a doctor looks at your lung X-ray image and says you have COVID-19, then the doctor also will explain you, right? That okay, do you see here there is a lot of uh, white patch. That means your lungs are filled with some kind of water or you know some other substance. Hence, you are COVID-19 positive. And if you give the same image to your algorithm, it will just say that, hey, you're COVID-19 positive. Then would you rely on this? No, you need that explanation, like doctor has explained you on why it is COVID-19. You want your algorithm also to give you details on why your algorithm thinks that you have COVID-19. That's called as explainable AI. And this is a very hot area of research currently as we speak. And for that purpose, we are going to use a few things. Of course, I'm not going to go line by line here because it doesn't warrant that detailed explanation of the code. But let me explain what we are going to do now. We are going to quickly, until 125 or so, we are going to understand on how do we visualize intermediate layers. Because it is black box, at least we need to visualize what's happening there, right? So you have your image, you have your conf pool. What is the output of each of these images? How is it going to look like? What features are getting highlighted? What features is your model learning? Okay, that is what we want. So for this, I'm going to load the model. Okay, and this is a model that we are learning. We have all the convolution, max pool, conv, max pool layers, then flatten, dropout, and this. And then I'm taking just one image out of all the images that we have, only one of the images of cat. And we are going to process that and we are going to visualize it. This is the image. Okay. What we shall do with this image is we are going to look at 8 different layers, top 8 layers. Okay. And we are going to view the output of those layers. And we'll at least first get started by looking at the first activation layer. And let's see what is going to happen here. Okay, we have run this. Now if I do a plot, it will show you the activations. First, let me plot the um, activation. Look at it. What features is your model trying to learn? Maybe the edges. Here also it's getting highlighted. This also is getting highlighted. Let me choose a different color. This part is getting highlighted. The edge here, edges. So maybe this is in some sense capturing the edges. Maybe. It's black box. At least to some extent, we can make out on what portion it's going to, it is actually highlighting. So here when I say 4, we are trying to look at the 4th channel of the activation. There are many activations, right? Many functions that you're using, many layers. So if you see here, there are 148. Sorry, 148 by 148 by 32. Sorry, 32 channels are there. So those many convolution layers you applied. So at least a few we will visualize. Here, let's visualize the 7th one. This is highlighting something else. Where is it focusing? Maybe, I don't know. I'm feeling that it's highlighting this ice to a great extent. Okay. So it could be maybe the blob kind of functionality which is getting highlighted. Now, if you want to visualize all the different layers, do it. This is the code. Okay. But as I've told you, I would not like to get into the depth of that because it's not needed. Look at it. Initial layers are capturing some features. Then what's happening? Then you're doing a max pull, so you're reducing the size of the image. Then again, you're doing a conv 2D. Some other interesting features are extracted. This image, something else. Here, something else. Okay. And then again, you're doing a max pull, reducing the size of the image. Again, you're learning something. And as and how you keep moving forward, the kind of representations that your model is going to learn, you're clueless. Black box. Here is where people are working. And they're trying to make this explainability become a reality. Look at that. It's just reducing the uh, explainability part. This is what happens. Okay. Not just the output of your convolution layers, you can also visualize on what kind of features your model is learning in terms of your convolution layer in itself. Let me run this. Sorry, but this entire thing is too complicated, so I'll just run it and then show it to you. My God, I expected something of that kind to happen. Okay, next week when I run it, I will debug it and show it to you. And one final thing that I want to show you is, if I'm taking an image, say, then if I want to predict on what that image is, and then overlay a heat map on top of that, how is it going to look like? Let me explain this part because this is important. In cancer prediction, etc., this will come in extremely handy. Okay, but the previous thing we were getting an error, right? I'll fix it. No worries. It's just about version upgrade, different versions, etc. Okay. So to explain you about this, I have to say that using these lines of code that I'm going to explain now, some amount of explainability came into picture. And people used a technique called as CAM visualization. CAM stands for Class Activation Map. Class Activation Map. What happens when you use this class activation map is it is going to take your image, input image, and then it is going to highlight on which portion of your image is highlighted to classify that this is a specific image. So let me import this VGG16 and I'm just importing Kerasa's backend. VGG16 weights equal to ImageNet. Okay, so you just take the weights and you import the required modules and you're importing an image which is called as elephant image. Okay, I can go here and show you that image basically. Okay, we'll take this, what is the name of that, elephant.jpg. Yeah, we'll take this image as an input. Okay, and what I will do is I'm going to figure out which image this is. Okay, what image is this? I want to classify. So what I will do is now I'm going to pre-process the image and I'm going to predict. We already built the model. So we are going to pre-process the image and then we are going to predict on what is the image basically. So there are a lot of predictions which have come in. It says that there is 90% probability that this is an African elephant, 8% probability that it's a tusker. There is probably 0.4% probability that this is Indian elephant. Okay, you're just looking at the top 3 predictions and you're saying take the maximum argument, maximum of the prediction. So it says, okay, the maximum prediction says that this belongs to 386 class. Index number 386. And in your ImageNet competition, VGG16 that we are using is built on what? VGG16 is built on ImageNet. And when you look at that ImageNet data, it has 1000 categories. Out of these 1000 categories, category number 386 is African elephant. Cat, dog, mouse, horse, house, car, bus, building, humans, all those categories were there in these 1000. Out of that, 386 is African elephant. Now what we want to do is, we want to look at which portion of the image here. Did I close that? Okay, let me run it. So which portion of elephant is getting highlighted to say that this is an African elephant? If at all, say for example, this grass is getting highlighted to say that this is an African elephant, would you even rely on this model? No. Even if the prediction is right, you will not rely. If it's going to highlight this portion, probably a sky, would you predict, would you rely on this model? You will not, because your thoughts will be like, hey, it highlighted grass, then why is it saying this is an African elephant? Or it has highlighted sky, but how can it say that it's African elephant? In that way. If it's highlighting some portion of this or this elephant, then you can claim that this is reliable model because it is highlighting the right patches to decide on whether this is elephant or not. So the next lines of code will actually do exactly the same. Okay, and you are going to get a heat map. Look at that heat map. So it says that, do you know what? This portion of your image that you have is getting highlighted. Hey, what is this portion in this image? I don't know now. Okay, this portion means what? Is it this portion or is it this portion? Or is it this portion? I don't know. So what do we do then? I am now going to overlay. I'll use the computer vision aspects and we are going to take the image and we are going to overlay the heat map on top of this image. Okay, we'll do that. Let me run it. Superimpose. Once you superimpose, you can write that to this folder. Let me highlight it. You're taking the superimposed image and you're saving it here, okay, in this folder. So let me go back here. Hmm. I don't know. So let me do one thing. Let me take this path AI and let me have this image saved here. The path itself is not existent. Why create a new path now when we have this? So let me run it. True. So is it saved here? Let me see with the date. Wonderful. At 1:37 today, it got created. Wonderful. So look at what has happened. You have this, and then you have this. Very clearly, it says that to classify this as an African elephant, this portion of the image was highlighted heavily. Also, this portion, that heat map. So it's highlighting the right portion. So would you rely on this model? Oh yes, absolutely you will rely on this. This is exactly what we have done with respect to the cancer prediction model that we have, that I've just shown you, or any other model that we build. This is exactly what we do. Heat map is like heat. What do you have on heat? Fire. What colors will you have on fire? These kind of colors, red, yellow. Okay. Yeah, we will see on how best we can supply you with the code. For now, use this video and replicate it, then we will see how to give it to you. Yeah, sure. So I think the attendance form is already available. You can take that attendance form. Okay, I'll ask our team to keep posting the attendance link here. Feedback we will collect on the last day maybe. Okay. Any questions, friends, that you want me to answer? Attendance form is put. Yep. Enoch also has shared that. Today's program, where do you get? It is there here in the YouTube link. Sure. We will put that in GitHub and share it. Shubha, if you're there, let us do one thing. Let us share the GitHub details also so that our people might download. Both Sunkara, Nagendra, both will work. Both VGG and LXNet both can work on your RGB and grayscale, etc. If you have attended the previous sessions, you know by now that grayscale and color there is no big difference. When you segregate the various channels, you get the grayscale only. Uh, Lakshman, you can read Andrew Ng. Andrew Ng is a like father of deep learning. You can read his books. Aparna, next week probably it will make more sense because we'll be working on sequence data. Sure, Srinivas. If possible, we'll include. Thank you, Humera. We'll put it on a WhatsApp group, Kanaka Kumari, and then you can access that. If the data is more, you need not use it. But if your model is overfitting, then you use it. Anantanath, sorry. No, you need not convert color images to grayscale. Automatically, your algorithm will take care of that. For that, you will have to look at OpenCV, JOS. You can apply. See, artificial intelligence deep learning is something which can be generically applied to all the industries, all the sectors. Again, you want us to share, is it? Feedback link or attendance link? We will be sharing the attendance link here. Thank you so much for your feedback. It really means a lot. Maybe sufficient, may not be sufficient, Jagdish. We cannot say in that way. It may be sufficient for certain scenarios. For certain scenarios, it might not be sufficient. Both will be equally good, Sendil. We can do. We have already done analytics on whether someone is shopping or stealing, Ramakrishna. Tracking the Kalman filter. You can. Kalman filter also is something which is fast picking up. You can use that also. Aparna. Quiz will post on the WhatsApp groups. Andrew NG. Preeti Gupta. You can read that. But after reading that, don't complain to me saying that it is difficult to understand. Books are there, umpteen. Andrew NG is something that you can read. You have machine learning using R, machine learning using Python, books which are publicly available, Jayanti, you can read that. The 3D images and all that, we don't have sufficient RAM available, Chakrapani. RAM and processing is not available. So slowly they are also working, your NVIDIA, Intel, they're working on the chip enhancement also. That's what it means. Yes, it works, Siddharth. Yeah, sure. Why not, Suresh? Absolutely. We have those plans. Not exactly which I remember about publicly available, Sridevi, but you can do a Google search and you can try out Agriculture University images. IIT Hyderabad, Agriculture, Rajendra Nagar Agriculture University data, and you will find something because I personally was involved on that project. But it's there on IIT Hyderabad archives. Yeah, multiple objects also can be tracked. Adinarayana. Whenever you have less data or when your model is overfitting, you use data augmentation, Sandhya. There is no specific book as such, Sujata, but you can just search on Amazon and purchase any book which has good reviews on Python. Edges, blobs, texture, motif, etc. are the images, interest points that you can extract from the images. Jagdish. Ravi Kumar, I think we we shared the link, Ravi Kumar. Again, do you want us to share? Okay. Again, I'll share it. Yeah. Enoch, can you just share your screen and write the phone number, a WhatsApp phone number to which they have to send message so that we add them to the WhatsApp group? Enoch?
Sure, Bernie. Let me do that.
Yeah, yeah. Please share your screen and do that.
Yeah,
Just type the phone number.
sure.
If you have null Santosh, then you have to do data cleansing first. You can do any book on OpenCV. OpenCV version 4. Now 4 is going on. OpenCV 4. That book will be good for you. Swati, we will learn on speech on probably the last day of the training or last but 2 or 3 days. Yeah, we'll learn. Certainly that would be covered. So we will be writing a number. Enoch, we are unable to see anything. OpenCV 4, yes, right, Pawan, Dr. Pawan, yeah. Okay, so
Can you
please send a WhatsApp message to this number if you're not part of the group and we will share the details. Suresh, yep, you have to install CUDA first. CUDA, and automatically it will configure for you. Suresh. Rainfall forecast model, is it, Ratna Kumar? Then you have to use RNN model, which we are going to discuss later. Any other questions? No, there are no, we will not be sharing any assignments because there are no assignments which we are giving to you. We are giving you all the training slides and the quizzes, and the recorded videos are given on YouTube, Sandhya Rani. So no assignments. Then I need to take access of your screen and do it, Harshavardhan. It's all about computer installation and all that, right? So you can do a Google search and solve it. Okay, Harshavardhan. Otherwise, different computers have different issues, and I'm not a network engineer or a system administrator, right? So it'll be difficult for me also. I also do a Google search and solve it, Harshavardhan. So you can do a Google search and solve it. Katepalli, please use your laptop to attend. That was a prerequisite. If you attend on mobile, you'll not be able to see Katepalli. I mean, how can I help? And there is no way to zoom the output. Okay, please understand. I request you to please understand Katepalli on that and attend from your laptop, then it'll be better. It won't give you good results, Ratna Kumar. You can try. That is research related, right? They have 5 years, 6 years time to research. It won't, it is until now it didn't give any good result. If it gives any, probably in future we'll learn about that. OpenCV is for image processing, CNN is for prediction purpose. Yep. Thank you so much, everyone, and have a good day. Have a great weekend. On weekend, you can watch our recorded videos and then make best use of it. Thank you all, friends. Bye. Yeah, for any forecasting, you can use that. Yeah, Leelavati. Well, we'll do one thing, otherwise, we'll share the code with you all. I think that should solve the problem. Because if you type that code by looking at the YouTube, anyways, you'll get the output on your system. Or I will give this exercise to you, Dr. Leelavati. Can you do that and share the Word file with me? I will relook at that and then improvise it, and let's together share it with the participants. Yeah. Hope that will be helpful. So yeah, next session will be on Monday. Okay, next session will be on Monday. Yeah, I request you all to do this. You guys run the code on your computers, take the output, save it on a Word file, and you can share it with me. I will do the required changes, amends, and then I'll put it on the WhatsApp group so that everyone gets access to it. Yeah, and I can share with you in private, or I'll put my email ID here. You can do that. Bharani at 360digitmg.com. That's my email ID. You can just drop in that and then I'll take it further. But it'll be a very good exercise. Absolutely very good exercise. All right, friends. Thank you so much. Bye for now. Take care.